What are we looking at? Oh, what are you looking for? Looking up there. All right. Very good. Let's see here. There we go. So yeah, example 5.8 is it cannot be. Now I showed you this before, but now we've worked our way to it. So it's d minus 1 times d minus 1 times d minus j. Right. Now the thing is about example 5.7 is if you were to look at that in what you might call standard form, so like this one, if you were to just write it out in terms of like prime notation, it's more clear from here what it is. It's actually, when you actually multiply this all out, the stuff with j's cancel out, it turns out.
Yep.
And you're in the end of it, you're just left with like a, let's see here, w, so this is, let me write that out, so that gives me like a d key by prime, and then I've got like,
yeah, it gives you that.
C here,
Well, I would say that's a repeated root with the y prime, yeah. Yeah, wouldn't you just add them, like, under normal differential equation strategies?
yeah, I mean, it's something like that. I could have done it wrong.
You would add a repeated root plus a characteristic equation.
Oh yeah, I mean, so either this.
Essentially what you did, yeah.
If we're working with the real variable t and this,
Yeah.
the real solution would look like that.
Yeah.
Of course, the form in the hyperbolic solution has the same form, really. It's
Yeah.
But this is what the differential equation looks like if you were to actually write it in quote-unquote standard form, right? Let's get it out. This one, on the other hand, so that's w prime minus j w, which gives me w prime minus jw prime minus w prime plus jw. Or if you like, it's w prime minus j plus 1, w prime plus jw equals to 0. So this is what that example 5.8 differential equation looks like if you put it into standard form. So I suppose we could say more concrete things about how it works for quadratic differential equations if we thought more about this, because there is a relation between the coefficients and the roots. You know what I'm talking about? Let me just write it out. If you have, we'll stick with monic. If you have x minus like root 1, I'll use alpha. X minus alpha 1 times x minus alpha 2, right there, right? You multiply it out, you get x squared minus, or let's say, we'll find minus alpha 1 plus alpha 2, right?
Yeah.
X plus alpha 1, alpha 2, right? So, funny. So if you say this is equal to like ax squared plus plus bx plus c, you know. Then you have, you know, things like b is equal to minus alpha 1 minus alpha 2, you know, and c is the product of the roots. A equals to 1, for a equals to 1, I should say. Otherwise, you have to divide by a and crap and junk like that. It's a part of the story, but.
Did we find a quadratic formula in the hyperbolic numbers?
I mean, not explicitly.
Okay.
So, what's interesting to me here is that, okay, so the theorem I have just erased, it says if the difference of the roots in the factorization is a zero divisor, is not a zero divisor, then we can just write down some of the exponentials as the solution, you know? But the funny thing here is that the difference, okay, so like the difference in alpha 1 and alpha 2 for my example 5.8 is what? Alpha 1 is 1, alpha 2 is j, alpha 1 minus alpha 2 is 1 minus j, right? But what's amusing me here is that the sum of the coefficients also ended up being a zero divisor. I guess that's just a quirk of...
Is j plus 1 times j plus 1 is 0?
No, j plus 1 times j plus 1 is 2. 2 times j plus 1.
Okay.
Yeah, we have there's a kind of funny formula. J plus 1 to the k is k times j plus 1. That's how it ends up working out. Weirdly enough. No, anyway, I'm sorry, I'm distracting myself with this. So, come on. Erase. So, this one, as I explained to you, I think, before, is we can't use e to the z and e to the jz. These are linearly dependent.
Mm-hmm.
So what we did was to go, okay, I'm gonna say d minus j acting on w. I'm gonna call that thing eta. So then I've got d minus 1 acting on eta equals to 0 by substitution. So basically I make a substitution and
Bless you.
yeah, cheers. And this is up here called star. So star gives me this. Now, so then this we know how to solve. We know this has solution eta equals like c1 e to the z, right?
Mm-hmm.
So then that brings us back to, you know, dw dz minus jw is equal to c1 e to the z. And then we have to solve that. Now there are various ways you could solve it. I used a kind of
Separation.
yeah, I kind of use like integrating factor technique. I guess I can do that again. So this is multiply this by e to the jz, I think. So you have e to the jz dw dz minus j e to the jz w equals c1 e to the jz e to the z. So this just becomes dz of e to the jz times w equals c1 e to the j plus 1 z. Now ordinarily I just integrate both sides, like you said, try and just, okay, divide by 1 plus j, but that's trouble because we can't, it's 0 divisor. So I'm forced to use series methods basically. So integrate both sides. I get e to the jz w. What I'm trying to say is I can't find the integral by the usual u substitution, if you will. C1 integral of e to the j plus 1z. Alright, but I'm going to rewrite that as the sum n equals 0 to infinity j plus 1 z to the n power over n factorial dz. And by the way, if I'm going to do that, I really should say plus a constant.
Yeah, I was working on this thing. I was just like, what happens if you throw it in a quadratic equation and you get nonsense? Because what's the square root of j minus 1? What does that mean?
Mm-hmm.
But the thing is, what you don't get is you don't run into a problem with 0 divisors. But you got to prove the quadratic even works in the hyperbolic numbers.
That's an interesting question, which is, well, I would assume that the solutions, excuse me, the solutions include 1 and j.
Yep. This is what, so I got minus a half times 1 plus j plus or minus square root of negative 2 over 2 times j minus 1, square root of j minus 1.
How do you do that?
Oh, no, I mean, this is an arbitrary, I used a real quadratic equation. And there's no quadratic formula. I just wanted to see what would happen, and if you could, but you do get an answer, it's just, you get an imaginary component which doesn't exist in the hyperbolic numbers.
Okay, I'll bite. What was the isomorphism from H to R cross R?
Yeah, that was my.
Oh, let me finish this,
Yeah.
and then we'll come back to that. So this, remember, is actually, this simplifies to n times j plus 1 z to the n.
Mm-hmm.
And so what I've got then, well, I mean, let me just go ahead and say n over n factorial is what? N over n factorial is n minus 1 factorial. And then I need to, do the term by term integration that I proved is reasonable in the previous paper. So I have C1 sum n equals 0 to infinity j plus 1 over n plus 1 times n minus 1 factorial z to the n plus 1 plus some constant.
Also, the other problem, hyperbolic numbers, I think is r cross r, and you get an imaginary root, so it wouldn't matter.
Yeah, I wouldn't know without working it out.
I'm just knowing by the isomorphism of the j number, like you get a negative number. And so it wouldn't matter, like you would be able to work it out. Unless like you think of a technique where you could have a negative number. But yeah, with or without the isomorphism, you get a -2 under the radical. Or you could pull it out. Or you could pull that out. I'll get back to you. No, you can't. No, you cannot pull it out. Or, get that -2j. If you just leave that, you can do 1 plus 1 minus j, and you get rid of that. So you get radical 2. If j plus 1, whatever the isomorphism is greater than 0, it would work out. But yeah, so we're here.
Yeah, I'm just, let's see here. Oh, I'm sorry, I had to, I see I made a mistake. I always fuss at my students for not checking the integrating factor method. So I am victim of my own criticism. This is not that. Because if you differentiate this, you get j e to the jz. Minus, so I need a. Minus. Alright, fine. So I don't think what I had written was wrong. I just try writing it again. 1 minus j. Anyway, the point is, this is all right. So n equals 0. We put n equals 0, this is just 1. So we start with 1. And then plus the sum n equals 1 to infinity. This I had not broken this out explicitly last time, but now n equals 1 to infinity. The thing is, this j plus 1 to the n is n times 1, j plus 1. That's true for n greater than or equal to 1. N equals 0, that's not true. N equals 0, it's not true that 1 equals to 0. So that pattern, I get a split off n equals 1 and going on. And now there, 1 minus j, I think it's also true for 1 minus j. Let's try this out. 1 minus j squared, what do you get?
0. Oh, yeah. Oh, 2.
So you get 2. So the point is I can simplify that to n times 1 minus j z to the power n over n factorial. And I'm just not even, the c, when do you want to add the constant, you know?
Yeah.
Okay. I'll let the constant be in here implicitly. All right, so then this and that gives you the n minus 1 factorial that I have in equation 68. So this and that simplified n minus 1. When you integrate term by term, you get n plus 1 in the denominator, so you get, c1. The 1 is interesting because it integrates to z. That's kind of the thing I think is most interesting here is that 1 actually is very interesting to me. So that 1 gives me a z, and then this, it integrates to some mess. All right, it's the sum n equals 1 to infinity of, let me pull out this, go ahead and pull out the 1 minus j. So 1 minus j, all right, times the sum n equals 1 to infinity of, z to the n plus 1 over n minus 1 factorial times n plus 1. So if you want, you could also write that as n over n plus 1 factorial. You could rewrite this as n over n plus 1 factorial if you want. I'll go ahead and do that this time. And then, of course, since I've actually done the integration, plus c2. All right. But of course, c1 times c2, I mean, you can kind of like go, okay, I'm going to erase this, I'll put this here, and I'll just call that a separate constant c2 independent of the c1. It's the same difference. Then you take this, and you multiply that e to the jz on both sides. What does that give you? C1z e to the jz, right? Plus 1 minus j, e to the jz times this funny function. N equals 1 to infinity, and z to the n plus 1 over n plus 1 factorial. Plus c2 e to the jz. So I think I told you before, I'll tell you again, I thought this was really, really cool when we found it because I'm like, oh, so it's like the repeated root case when the difference of the roots differs by a zero divisor. The solution resembles the repeated root case.
Yeah.
Twisted a bit. So like just this and this is what we get. That would be just straight up the solution. If I had d minus j squared acting on w equal to 0, right?
Mm-hmm.
Then by things we proved, e to the jz and z e to the jz, that would be our fundamental solution set. All right, those are linearly independent, but we don't have that. We have d minus 1 and d minus j, right? So we get something that's perturbed a bit from the z e to the jz term. We get this extra piece, and the extra piece, notice, I think interestingly, comes packaged with a zero divisor. So in this approach, if the difference of our roots is a zero divisor, then we have kind of like no choice but to do the substitution strategy and integrate our way up. And in the process of that integration, we're going to pick up like novel terms that correspond to the zero divisor which are present. I don't think I've pushed that method of calculation much further than this example, though. So, and it's not particularly interesting to me to do that because, again, I soon find a much, much better way. And finally, this method altogether is really incomplete because Even in the real case, you know, if you have d squared plus 1, you can't solve it by our method here. Because d squared plus 1 doesn't factor over the reals. Right, so you need to pair this technique with some sort of complexification idea to get the full story.
Yeah, that's what I ran into when I was chugging it in.
So what was the isomorphism? I'm kind of curious about this though.
It's R cross R, right?
Yeah, H2.
And it's like either 2 pi over 4, either 2 pi over...
Oh, no, it was simpler than that. Like it's psi of x plus jy is, I want to say it's x plus y, x minus y maybe. Because then if I do psi of j, we get 1 minus 1. If you do psi of 1, you get 1, 1, which is the identity. I think that's it. This is the isomorphism. The inverse has the halves in it.
Yeah. So you plug a...
So what is this? You want to look at the characteristic equation?
Yeah, that's what I was doing.
So we have
get,
z squared minus j plus 1 times z plus j equals to 0. So feed that to your side, right?
Mm-hmm.
So this is actually x squared plus y squared plus 2jxy minus j plus 1 times x plus y plus jy, right, plus j. So what it was gives you x squared plus y squared. J times, that gives me minus y. See that? This?
Yeah.
Minus y minus x. Is there anything else that's real? Nope. And then plus j times 2xy plus x, minus x, right? Minus y plus 1. So there's your quadratic. There's this equation in explicit, like, real substructure, the underlying real equation in terms of the real and imaginary component of the hyperbolic variable z. And if I this gives me the corresponding, man, why did I do that? So sorry, let me try something else here. I mean, this is not wrong, but it's not helpful. So let's let psi of z equal to, say, whatever else, w maybe. Then this gives us, take psi of that, we get, I think this is what you're doing, which is w squared minus psi of j plus 1, w, plus psi of j equal to 0. So that's w squared, now it's j plus 1, gives me 2, 0. J is 1 minus 1. Now, the w we could write as like w1, w2, or whatever you like. I mean, you want to use u and v?
I mean, we gotta solve the equation separately anyway, so you can just really write equation A, equation 1 if you want to.
I'll use u comma v then. So this is, we've got ourselves u squared, v squared minus 2, 0 times uv plus 1 minus 1 equals 0.
Alright, then just break that down into 2 equations.
Right, so we got u squared minus 2u
Plus 1.
plus 1
v squared minus, v squared
plus minus 1. See, I knew that's where you get into trouble.
Right.
And then this characteristic equation should just be square root minus u minus 1 squared.
Yeah. Mm-hmm.
And it's like what? C1 e to the minus t.
Oh no, this is just a real equation, so this is easier. This is just u equals to 1 twice.
Okay.
And this is...
You have to complexify that. No, you don't.
No, so we get, just to summarize here,
Yeah.
we get
You get 1.
u equal to 1, v equal to plus or minus 1.
Yeah.
So that gives me w equal to 1, 1 or 1 minus 1, which when you do the inverse map, you get to 1 or j. So in fact, the good news, the solutions which were apparent almost from the beginning,
Mm-hmm.
because this gives us the factorization
Yeah.
of x minus 1 times x minus j for the underlying polynomial, or rather z minus 1, z minus j, whatever letter you want to use. The point is the solutions to the roots of this polynomial, if we think of it as a polynomial, not a differential equation, are 1 and j.
Mm-hmm.
And that's actually it. It's not like there are others. This one over here, if I looked at the equation x minus 1, x plus j, x minus j
Mm-hmm.
equal to 0. Yes, that has solutions 1, minus j, and j, right? But because of this, right, because you can rewrite this, in fact, as x minus 1 squared times x plus 1, it is then manifestly clear that this also has solution x equals to minus 1, also solution.
Yep.
And the minus 1 solution was not apparent from this one.
Yeah.
So this is a third order problem that has at least 4 distinct solutions.
Give me a sec. I'm not disagreeing with you. I'm just trying to see if you can see that.
Now I'm not saying that's all the solutions there are. I really don't know. I haven't
No,
studied
if
these
you
things.
did that isomorphism to H, you would get 4 solutions, I think. Because you get the 1, 1. So, well, what would you do? Well, no. I don't know. Hold up. Oh, this is your advisor. Wait, but could that equation even happen? Like, why can that equation happen?
What equation?
Not equation, but why can that differential operator even work out? Because it's zero divisor.
I don't.
D plus j times d minus j, like you can factor that like a normal.
But it's not 1 plus j, 1 minus j. I mean, it's the...
Yeah, that's right.
No, that is why I looked at that example, because I thought maybe it would be interesting because of that kind of analogy, but I mean, it was interesting, but it's not as sort of, what's the word? Groundbreaking is example 5.8, I suppose.
No.
Now, example, so like next up we have section 5.2. So, I mean, that's pretty much all I've got to say about the operator factorization. If you can find them, and they're like just, they're not, if you can find them and the factors you find are not, they don't differ by zero divisors, then pretty much just like normal. But if they do differ by zero divisors,
Yeah.
we got calculations to do. Now, solution via isomorph, and again, we're still stuck on polynomials which don't split over the algebra.
Okay. You hit record, right?
Oh.
Or eraser on the board.
I did.
Okay.
We're actually 35 minutes in.
Oh man, pause.
So solution by isomorphism is, I suppose that, like in this section, I suppose that I have a way to break the algebra as a direct product of k algebras. And then what I do is I argue, okay, if that's the case, then the matrix representation is the direct sum of the matrix representations of the algebras. And you can express the... this section is actually useful, and it gives you a calculational overlay for how we can do calculations in direct product algebra. I actually lay out here how you can decompose the variables in the direct product algebra as a sum of variables in the subalgebras. So if you've never worked before with this kind of context, like there's a lot of calculational wisdom in this section, which is useful. Although I think the actual result of the section, I don't know, I mean, it's I guess it's got its place, but I'm still fond of the section that follows. But, so like equation 74, I'm saying like zeta sub j is written in terms of x1j through xn sub j, comma j. So like the x's are real variables, the zeta sub j's are algebra variables, and the sum of the zeta j's, see that 73? Equation 73 gives you like the total algebra variables is built from, you know, the sum of these k zeta I variables. Anyway, all of that together, what happens is that the Jacobian in such a scenario is block diagonal, because the if you have differentiability with respect to the algebra, you have like the Cauchy-Riemann equations only mix together the variables in each of the subalgebras. We've already seen this kind of pattern in the direct product algebra where like, so let me just, rather than, let me kind of give you an example of what I'm saying in 76 without getting into all of the index chasing, okay? So if I had my algebra was equal to something like, say, complex cross H3, all right? Then what I'm saying is that the variable in the algebra zeta can be written as like E1 zeta 1 plus E2 zeta 2, or if you like, zeta 1 zeta 2, where zeta 1 is something like, you know, x1 plus I x2. Actually, I think my notation is that this is x11 plus I x12 if I'm a slave to the notation that I set forth in this section. And zeta 2 is something like, it's got substructure. I can write it x21 plus jx22 plus j squared x23 if I use the standard 1j squared basis for H3. So this one variable in A is actually corresponding to 5 real variables. And if I looked at it, if I looked at a function which was a differentiable here, right? If I had a function which was a differentiable, and if I like write that function as say f1, f2, where of course here, you know, f1 is this complex value, and f2 is h3 valued. And then the Jacobian of f, it's going to look like the Jacobian of f1, the Jacobian of f2. And okay, generally speaking, there would be non-zero stuff here and here. But if it's a differentiable, then these are 0, all right? And
so that pretty much proves you
Well, I don't think that matters.
Well, these are a differential, and for my specific example right now, it's complex, so this one looks like, you know, a b minus ba, and it's a b c. Let's go c a b, b c a. I mean, that would be the pattern for the Jacobian, if it's a differential. Okay. So essentially, the story for what a-differentiability looks like for direct product algebra, it's naturally assembled from what we already know about the products forming the product, like any of the factors forming the product algebra. If we understand the shape of the Jacobian for those, and the Cauchy-Riemann equations for those, there's a natural extension to the product according to these rules. And so that's what I've said there. Now, let's see here. So my proposition 5.10 is a summary. If we have a function which is a-differentiable in the product algebra, and we can write it as, you know, a vector of functions in each of this. A vector of functions where each function is from the subalgebra, defining the algebra. We write the derivative as, you know, basically form the total derivative from the derivatives with respect to each of the subalgebra variables like that. Then in a nutshell, so for example, so the question is, what does a derivative look like in one of these product algebras, right? If you have a function which is a-differentiable in the product algebra, what's the derivative look like? Okay? So, example, if your function is f1, f2, right? The direct product algebra, then df dz, what is that? That is the differential of f acting on 1.
It's just the identity, right?
Which, well, this is, you could look at this as df acting on 1, 0 plus df acting on 0, 1. So this is partial f partial x plus partial f partial y. But remember, f is actually f1 and f2, and what do the Cauchy-Riemann equations tell you here? F1 is just a function of x, f2 is just a function of y.
Yeah.
So this we could really just rewrite as
The derivative of f1 times plus the derivative of f2.
right, so this is df1 dx 0 plus 0 df2 dx, because the other zeros are the Cauchy-Riemann equations, dy rather. In short, what we got here, let me just make the summary. The summary is that df dz is exactly df1 dx df2 dy. What I explain in this section is the same is true if you take the product of k algebras. For example, up here in this 5-dimensional algebra, if I was to have a function that has f1 and f2, where these are like the component functions with respect to the complexes with respect to the hyperbolics, and you calculate df d zeta, let's say. So I will eventually today write a proper zeta. Anyway, then that is going to be df1 dz, complex derivative, and df2 I guess I'll use eta here for lack of imagination, where eta is the 3 hyperbolic variable. It's actually very simple for a direct product algebra. If you take the derivative, you just differentiate each component function for your algebra function.
By that algebra.
By the algebra variable. What could be simpler? It's just that.
Which is quite nice, bro.
Yeah, it's not bad at all. And I derived that here. And also, other things are really nice. Like if you have zeta to the n, if you have a polynomial in the direct product algebra, if you're like zeta, which is zeta to the zeta 1, zeta 2, zeta k, right? And you raise it to the n power, what do you get?
You get each one of these components. Why is that?
Yep. Just like that. Just like in the direct product algebra, we have xy times xy, right? You get x squared, y squared, and that I mean, it's kind of actually kind of funny. Like intuition you gain about products from the direct product algebra actually serve you pretty well for higher products, even though r cross r is such a simple example. So what that means is that if you take a polynomial, this is like in equations 81 and 82, saying if you have a polynomial in the direct product algebra, it gives you a vector of polynomials where each one is in the subalgebra, and so likewise you can take the polynomial and the differentiation operator and get a vector of polynomials in each of the differentiation operators of the algebra. So it's like the way the polynomial over the direct product algebra is, it just like naturally descends into a vector of the same polynomial in the derivative of each of the algebras that you're taking the product of. And so that gives us theorem 5.11, which says that you have a solution to P of d w equal to 0 if and only if you have every component, so like a differential equation on the product corresponds to k differential equations. But notice now that these are not real differential equations. In principle, these are algebra differential equations, one for each of the algebras forming the product. But in order to have a solution to the product, you need to solve each component at the same time, all together, all at once, to get a solution to the product. This is what theorem 5.11 says. And so that like equation 83 right there pretty much is why, because if we have P of D acting on W, it's the same as P1 D1 acting on W1, P2 D2 acting on W2 all the way down the line. So in order to get that equals to 0, it's going to be true if and only if each one of those components is separately 0.
usually the algebra is not manifestly a direct product, hence we have to filter calculus through the connecting isomorphism.
Right. So like what if you're, so I mean the theorem that I just mentioned to you, theorem 5.11, it's directly useful if your algebra is manifestly a direct product, right?
Mm-hmm.
But if it's just isomorphic to a direct product, then you kind of need to like filter the theorem through the isomorphism. And what I mean by that is theorem 5.12. So you have a solution over the algebra A to a given differential equation if and only if the W, which is equal to psi inverse composed with eta composed with psi, is a solution to the corresponding differential equation in the B, the isomorphic B algebra. So here we're assuming this is actually using the you remember that picture we drew between isomorphic algebras and like.
Yes.
Yes, it's that's sneaky stuff again. So if I have an eta to the n, a2 eta prime prime plus a1 eta plus a0 eta equal to 0. So here is over a, and psi is mapping the isomorphism from algebra A to algebra B. Algebra isomorphism. Eta is solution to star. If and only if psi of eta equal to, let's say, I guess psi of eta equal to W solves. So it's psi of an nth derivative of W. Psi of a2, W prime prime, plus psi of a1, W prime, plus psi of a naught, W equal to 0. In other words, and that's useful because, you know, we have isomorphisms in direct product algebras for many of our examples. So like, so I think it's interesting to actually look at this for, so the thing we couldn't solve by the usual techniques, thing we had to use series integration to solve was this one. We had d minus j acting on eta equal to whatever it was. Well, it's oh, excuse me. Sorry. That's what I want. So I want t minus 1 plus j acting on eta equal to 0. I guess what I look like. Look at in this example here. So I just was taking this as a trial example, you know. So we're looking at eta prime minus 1 plus j eta equal to 0 in H, right? So we let, you know, look W equal to psi of eta, right? Where psi of x plus jy is x plus y, x minus y, right? So what does that give us? we look at the isomorphic differential equation, we got what? We got W prime, right? What is, what's psi of 1 plus j?
So I have 1 plus j. That would be the 1 1 or the let's say identity would be
1 plus j. X equals to 1, y equals to 1, right?
yeah
So,
1 1 and 0 1 0.
yeah, so 1 plus 1, 2,
Yeah.
1 minus 1, 0, 0, and w.
Yeah.
So, now, I mean, we can solve that any number of ways, I suppose. I guess, I mean, one nice way is just that, okay, so then W is equal to e to the, 2 comma 0 times, let's say, s comma t times a constant, right? It's a C1, C2 constant here, though, right? Because we're in the direct product algebra. This is what C e to the alpha t looks like here, right? Alpha z, rather. Sorry. But explicitly then, it's W is equal to C1, C2 times, what is the exponential? How's the exponential work here? It is actually
10 and 0.
yeah, 2s comma 0, right?
Yeah. Yes.
So W equal to C1, C2 times e to the 2s, 1, I think. I'm using the exponential product is the product of the exponentials. That identity follows from the polynomial, this thing we've got of polynomials. Like if you think about what this means for exponentials, it means the same thing happens for exponential defined by series. So if you think about what happens to the series of the exponentials, it becomes a vector of series, which basically, among other things, gives you stuff like this. E to the xy is e to the x, e to the y for the direct product algebra. So I use that here to get this, which then, of course, then gives me W is actually like C1 e to the 2s C2, right? And then, let's see here, to get back to eta, what do we do? That's in the theorem. It's, oh, yeah. What did I say?
Oh no, it's psi times something times inverse psi.
Right.
So it's our normal song and dance for the pullback.
Yeah.
Or the composition of.
Right, it's kind of like a pullback here. So this is what we want. This is the eta. We've got here the W. This is
Psi.
yeah, psi.
Psi inverse.
Right.
So yeah, I think it's so psi inverse W psi. I think you wrote the other way around. But
It may have been solving for W. Let's see here. Is that right?
yeah, you solved for W.
So psi